Now here we're going to see an example where the limit comparison test doesn't quite apply in the way we've been using it. So this is going to be both conceptually a little bit interesting, and it will have some useful applications. So let's see both of that right now in this video. So let's consider a situation that's slightly different from the one that we saw in the limit comparison test in the first formulation of it. So in this formulation, what we're going to have is we're going to suppose that we have a series here with an and bn that are non-negative terms. That much is the same. But now, instead of having a limit equal to a constant that's non-zero, we're going to suppose that the limit is 0. Okay, so morally speaking, what that means is that when n is huge, an is getting much, much, much tinier than bn. So the upshot is, if the series bn converges, then it forces an to converge. Right? Because bn is much, much bigger. If bn converges, then a series of even much smaller numbers has to converge. Okay, conversely, if the limit is infinite, that means that, right, what that means is that an is significantly bigger than bn for large values of n. So then what that means is that if the series of the bn diverges, then the series of ans, which is worse in every way, right? It's bigger, significantly bigger, right? So if the bn's, the small series diverges, then an, the big series, has to diverge. Okay, so this is a useful tool in a family of examples. So let's consider here the series n equals 1 to infinity of natural log of n over n squared. Okay, so here we have the series from n equals 1 to infinity of natural log of n over n squared. And the natural guess is to say, okay, well, what happens as n goes to infinity? Natural log of n is not a p-series, right? It's not a power of n. But here's something important that you should know from Cal 1. Right? So from Cal 1, this is the so-called fundamental log limit. This says that ln of x divided by x to the alpha, if I take the limit as x goes to infinity, this is 0 for any positive number alpha. And actually this one is an easy enough thing to prove if you use L'Hopital's rule, and if you remember using L'Hopital's rule on that. I'll leave it for you as an exercise, and we can go over it if you don't remember how that works, because this is an important fact, and I want you to remember it, that the natural log of x grows much more slowly than any power of x, any positive power of x. Right, so here we have that this limit is 0 for any alpha positive, and if you don't remember this fact, I do encourage you to make a note of it and remember it. Okay, so now using that, what that tells us is that the natural log of n grows more slowly than any power of x. So we can say that we can compare, right? Then the idea is to steal some of the n squared. Right? So we can steal some power from n squared to kill the natural log. Okay, I'm sorry about this, the violence of this language, but what we're going to do then is we're going to write this as natural log of n divided by any power you like. I'm going to take 1/2, but you could take, 1/3 or whatever. And then we're going to write this here as n to the 3/2. Right, so we have this series n equals 1 to infinity ln of n over n to the 1/2, and then here we have 1 over n to the 3/2. And so this bit right here is of this form. Right, so that guy goes to 0 as n goes to infinity. And then we're left with this term right here. Well, that also goes to 0, but that one is a p-series. Right? So what we did was we split it as something going to 0 times a p-series. And that's precisely what we need in order to use this other form of the limit comparison test. Right? So what we're going to do is we're going to compare with the series n equals 1 to infinity of 1 over n to the 3/2. Okay, so good. By the p-test, we have that this series from n equals 1 to infinity of 1 over n to the 3/2 converges. And here what we're interested in, we have this series n equals 1 to infinity of natural log of n over n squared. So now we're going to use our limit comparison test to figure out what's going on. We're going to look at the limit as n goes to infinity. We're going to take our series, ln n over n squared, and we're going to multiply it, well, actually we're going to divide it by this guy, and we're going to divide it by 1 over n to the 3/2. So this gives us the limit as n goes to infinity of n to the 3/2 times natural log of n over n squared. So that's the limit as n goes to infinity of natural log of n over n to the 1/2. And by that limit we had on our previous page, right, but that fundamental log limit, this thing is going to go to 0. So this is one of the key places you really need to know this fundamental log limit. And so this thing gives us 0 by what we just saw. So what that means is that this numerator here, this guy, is much, much smaller than that denominator. Right? And that's good, right? By the limit comparison test, by the second form of it, we now have that the series where we go from n equals 1 to infinity of natural log of n over n squared converges. Right? Limit comparison and then combining that with that p-test. So most of these examples where you're going to want to use this, you need to think a little bit about using a natural log and the fundamental log limit. That's going to be the most typical example of the kind of problem that we'll have where you use this form of the limit comparison test.